All right, well, thanks everyone for joining us today. Again, this is Mike Mazzarese with AST Environmental. And today we have a presentation for you, a webinar that's going to be given by Mr. Kevin French from Vertex Environmental out of Ontario. It's going to be about a 25-30 minute presentation with Q&A afterwards. So if you do have questions, drop down menu. We're all pros now at using the format, so go ahead and send those and we'll answer those at the end. This presentation is also being recorded and will be uploaded to the AST website within the next week or so. And this is the first in a summer series for us, so keep an eye out for future newsletters from us. We're gonna have a series of topics over the course of the summer. So this is glad to have Kevin here to help kick us off. So Kevin's Vice President of Vertex Environmental, has over 30 years of experience and expertise in environmental engineering, specializing in site assessment and remediation. He's been involved in design and implementation of remediation programs across Canada, involving PRBs, adsorptive technologies, ISCO, and reductive, aerobic, and anaerobic biodegradation, groundwater, and bedrock for a variety of contaminants, including petroleum hydrocarbons, chlorinated solvents, heavy metals, and others. He holds a bachelor's degree in engineering from the University of Waterloo and is a professional engineer and a qualified person in Ontario. So Kevin, thank you for guest speaking today, and I'll just turn it over to you.
Okay, great. Thanks, Mike. Welcome everyone to this webinar. Today I'm going to be speaking to you about permeable reactive barriers, or PRBs. They've been around for a long time, but they just keep getting better. So this talk will hopefully give you some insights on how things have improved and how to make your PRBs even more capable and certain than they've ever been. So here's a bit of a presentation overview. I won't go through this in detail, but I'll touch on a few things. There's a brief history I've put in here on PRBs, and then we get into sort of the input parameters that are required to design a PRB properly. So your site characterization, if there are data gaps that are identified, there's some alignment profiling activities that could be undertaken. We'll get into a discussion of some of the latest PRB remedial amendments, and then some things that you can undertake, sort of an added benefit to improve your design, such as bench scale testing, sensitivity analysis, and then we'll jump into the actual installation techniques. And finally, some new developments in QA/QC testing, because there's no point, let's face it, in characterizing your site and designing a PRB, installing it but not installing it correctly and having it fail. So QA/QC testing is a critical part of the process. So as Mike said, my name's Kevin French. I'm a professional engineer here in Ontario. I've been in this game since 1988, doing remediation consulting work, and over the past 10 years or so doing the contracting side of things. Vertex Environmental, if you're not familiar with us, it's a specialized in situ remediation firm that started in Ontario back in 2003. So we're coming up to about 20 years of business, and started out doing primarily ISCO work, but then has expanded over the years into also ex situ systems such as water treatment, multi-phase vapor intrusion, and also high resolution site characterization. You might be familiar with that, but I'll talk about it in the context of PRBs in a little more detail later. Just an overview of the types of services we get involved in. And I'll talk about bench scale testing and remedial design, because that's really some components that can be critical to designing an effective PRB. So a brief history of PRBs. If you want to look at sort of as an evolutionary scale, I've characterized the old school way of doing PRBs, and this is sort of back in the mid 90s as this period, and this is about where we are today. So we've come a long way. I think there's still some room for improvement and refinement of these designs, but the PRBs are way better than they've ever been. So just to touch on a couple of trends overall in remediation as a background approach, there's many ways you could look at to manage risks or remediate your site. This is just a list of maybe the more common ones, and things have been changing over time. So, you know, excavation offsite disposal, I think, is decreasing over time, and that's driven by cost as well as sustainability factors. We've seen a real switch in Canada. You've probably seen it in the US as well, away from chemical oxidation and more towards chemical reduction. Just being, maybe it's not as fast, but it's more effective and long lasting as a technology. Similar with bioremediation, a switch from aerobic to anaerobic. And that's driven mainly by, as well, effectiveness. You know, if you think about dissolved oxygen, it's not very soluble in water. It's hard to get a lot of oxygen into the subsurface and maintain it, but it's pretty easy to get something else like sulfate or nitrate as a terminal electron acceptor into the water, and longer lasting and better distribution. So we've seen that swing happen. Lately, we've seen a big upswing in risk management and risk assessment. So a big part of that is developing site-specific standards for your contaminants, and then vapor intrusion mitigation, because in many cases there is no direct pathway to a contaminant short of inhalation. So vapor barriers are on the upswing, and in conjunction we've seen a huge uptake as well in both carbon-based injectables, which I'm going to talk about in detail, and of course the focus of this talk, which is permeable reactive barriers. Also another pretty critical risk management tool. So let's talk about PRBs. For those of you who are not familiar with them, there may be some of you out there. It's actually not like a physical structure like a wall. It's actually a zone, if you want to think about it that way, constructed underground that allows groundwater to pass through it. That's why it's called permeable. But then there's a remedial amendment built into that barrier, which reacts with the contaminants in the groundwater to either absorb or destroy or otherwise modify them, so that the water coming out the other end is treated to the desired limits. So it doesn't redirect groundwater flow. It works passively. Which means that once these are installed, there's no ongoing energy inputs required to maintain them. They may require some replenishment down the road, depending on the type of amendment, but they do last a long time, and they're very passive. So a great technology to install at your site to manage plumes. And there's various ways of constructing these, and I'll go through some of those, but basically they can be excavated if you think about like digging a trench and backfilling it, or you can inject remedial amendments into the ground to form these zones for a PRB. Why would you need one? Well, basically they provide property boundary control. So if you've got a plume of contaminated groundwater, maybe it's leaving your property, could be exposing you to liability that way, or maybe it's coming onto your property from an uncontrolled source and you want to stop that from coming onto your property. They're perfect for those. They're also used to cut off risks to sensitive receptors for using the same sort of technology and then approach. Maybe there's a litigation situation. But basically, they're not a source treatment. They're plume control. So they can contain plumes and treat plumes to prevent them from spreading and contaminating a larger area or an offsite area. So now I've called this sort of the old school way of installing PRBs, and really at the time it was the first ones were zero-valent iron. So the way these were designed is maybe you use there were generic assumptions or rules of thumb that came into a play. You dug a trench, intercepting your plume across perpendicular to it. You mixed up some zero-valent iron and some sand using these rules of thumb again. Maybe did some magnetic separation testing on them to characterize that the weight concentration was right. You backfill the trench, and then you hope for the best. So, you know, if it was under-designed or poorly installed, you had failure. If it was over-designed, maybe you wasted money on the remedial amendment. So either way, it was not good. But what if there was something unusual about your site? You know, something that ZVI couldn't address, some unusual geological or hydrogeochemical characteristics. Then what? You know, what you were very limited in what you could do. So the question, you know, is there a better way? Well, yes, there is. There is a better way. So just to go back and touch briefly on zero-valent iron, if you're not familiar with it, it's essentially elemental iron. This was discovered at Waterloo, where I actually live, back in the 1980s, that it served to destroy chlorinated ethylenes. And then there was a patent taken out. First so-called iron walls were installed in the 1990s. I believe one of the very first full-scale ones was in California. And they were at the time designed mainly to remediate chlorinated ethylenes like tetrachloroethylene or trichloroethylene, and heavy metals like hexchrome or lead, things like that, sort of multi-cationic heavy metal species. And the nice thing about zero-valent iron, I mean, it's been well established, it's relatively inexpensive, and it lasts a long time. So some of these original PRBs that were installed back in the mid-90s or early 2000s, they're still operating today and they're still effective. So proven sort of multi-decade longevity if these were designed and installed properly. So it's a great technology. But it does have its limitations, you know, in terms of what it can treat. And since that time, you know, there have been many new long-lasting remedial amendments that have been developed that can be used for PRBs for other types of scenarios and different contaminants, and most recently for some of the other organic contaminants like petroleum hydrocarbons. So as an environmental practitioner, you're probably much like we are here in Canada. The two biggest ones are chlorinated solvents and petroleum hydrocarbons. You know, the zero-valent iron works, you know, for many of these chlorinated solvents, but we really didn't have anything that was truly a passive reactive media that could be used in a PRB for petroleum hydrocarbons. But until we've had this relatively recent breakthrough of these carbon-based remedial amendments. And the one I'm going to talk about later on today is this one in particular, the trap and treat type of products, which combine the power of carbon absorption with a treatment mechanism. So you have a destruction pathway as well, and that's very important. I'll touch on that more later. In terms of designing and installing a PRB, and maybe the better way to do it, or what I think is the better way, I went back and looked at this sort of engineering design process. I'm an engineer, it's the way I think. And there are definite steps that you can use as part of this process. So to relate them to a PRB application, the question is, what is the driver or the objective for the PRB? So why do you need a PRB in the first place? Then you look at the characterization data that you have on your site. Do you have adequate information to do a design? Are there gaps of data that need to be filled in to improve your certainty? You can come up pretty quickly with some preliminary design options, and then maybe you need some more accurate or detailed site information in order to refine that design. You take a look at your remedial amendments. There are much better ones out today that are better engineered and designed for a PRB application. Maybe you need to do some bench scale feasibility and design testing to make sure that in theory, this design or this product will work for a PRB, but maybe there's something unusual about your site. It's got a fast groundwater flow, or there's a high mass flux across it. So maybe you actually have to do something a bit further to get some site-specific performance information. And then finally, make sure that it's properly installed, and you do your QA/QC testing. And at the end of the day, then ideally you have a PRB that is not only properly designed and appropriate for the type of contaminant and situation you're in, but it's been installed adequately, so it's going to actually perform as it was intended. So let's talk about the site characterization inputs you need in order to design a PRB. And I've broken this down into sort of a wish list package, if you will. So at a bare minimum, there are certain things that you need. So you need to know the contaminant type or types and concentrations, obviously. You need, and also the standard, the effluent standard you're trying to treat down to. You need to know sort of the physical dimensions of this plume. So, you know, how long does the PRB have to be? How deep is it to water? Where's the confining layer, so that you know what the saturated thickness of the reactive media has to be. So we need things like, you know, plume maps, borehole logs, so we know what kind of stratigraphy you're dealing with. And also sort of the other drivers are the receptors. So, you know, and so the receptors and the remedial objectives are kind of linked, but they go towards determining what degree of performance the PRB has to achieve. And are there any physical restrictions in terms of access? You know, is there overhead hydro? Are you right up against a fence line? Things like that. A building, you know, can you cut a trench open? Do you have to inject? Things like that. So that's sort of the bare minimum of the information that we need in order to design a PRB. An added benefit would be something like this. So, you know, a 2D flow map of your plume, your groundwater level contours, so that we know direction, maybe seasonal variation, and that is good information that will help us establish hydraulic gradients, combined with, you know, either estimated or measured K values. We know what the groundwater flow velocity then is, or the range of velocities. Which all leads into contaminant mass flux across the PRB. As I said earlier, you know, what's the base of the plume? Has it been vertically delineated? Is there a confining layer or not that we need to know about, that we can key into to cut off the lower extent of the plume? And then also sort of what the dynamic state of the plume is. Is this in a steady state condition, like it's a really old source of contamination and it's just reached steady state, continuing to migrate at a relatively uniform concentration over time? Or is it a fresh release and actually we're expecting worse levels of contamination to come across the barrier in the future? Or is it decreasing? Do we have a depleting source where it's actually going to slowly tail off over time? So that's also important that we can take that into account on the treatment side. For an injected application, is there a soil mass that's sorbed there that we have to take into account? Because depending on the amendment that you put in the ground, you may need additional to deal with the sorbed mass in the soil. And then lastly, groundwater field readings, things like pH, DO, ORP. You know, in many cases, the amendments that we're dealing with aren't overly sensitive to those, but if you have an unusual site with, say, like it's an acid rock drainage site with a really low pH or something else that's unusual, those field readings would be a good indicator of conditions that would need to be taken into account when doing the design. And then, as I've said here, sort of in a perfect world, you'd have a detailed conceptual site model. You'd have, you know, a 3D contaminant plume map. You'd know what your seasonal variabilities are. You'd know what your heterogeneities are in the subsurface, the range of hydraulic conductivities that we're facing and gradients. If it's a bedrock site, what is the fracture porosity and interconnectivity and orientation of those fractures? Because that's a much more complicated beast to tackle, especially with an injected PRB approach. You know, detailed geochemistry. Has there been some mass flux calculations? And then finally, you know, DO and DOC, because especially if you're dealing with some of the amendments that are carbon-based or iron-based, those will also exert a demand on the remedial amendments themselves. Okay, so PRB alignment profiling. In some cases, you may not know, or maybe it's only at a high level, you know what your plume looks like because it's based on a series of monitoring wells that are spaced out maybe, you know, 20, 30 feet apart. So for a site characterization, it's probably adequate, but for a PRB design, maybe it's not granular enough. So in that case, you can use what's called high resolution site characterization. These are direct sensing probes that can be used to gather a much higher amount of data in a relatively short period of time and for a low cost. So there's different types of probes out there. They're all direct push, at least the ones we use. And you might be familiar with them, but they measure things like presence of free product, hydrocarbon based. So if it's mobile or sorbed, it will pick up NAPL. Volatile, semi-volatile organic compounds can also be measured. Permeability of the formation and where the water table is. These have been around for a long time. Like we've had them in Canada here for 10 years. They've been around longer in the US there, and they've been used at literally hundreds of sites. So you may have run across them in your career. It's a very powerful tool. And I'll give you an example, a couple of examples of what you can do with it. So here are some representative output plots of the laser-induced fluorescence. So this is the one that measures petroleum hydrocarbon-based NAPLs. And what you'll get is similar like a borehole log, where you'll get a response, a relative response versus depth, which tells you, in this case, where NAPL or sorbed NAPL is present, and a relative amount. So the x-axis here is sort of a relative concentration, and the color is a simulated color that will indicate the type of hydrocarbon that's present. So in this case here, this is more of a diesel fuel or heating oil type signature. This is more of a kerosene type signature. It can also pick up like gasoline or even down into the motor oil range type of hydrocarbons. So if you imagine, a single borehole log, you're not going to have a lot of detailed information. Maybe you've got a description every 2 feet. Maybe you've got 1 or 2 soil samples per location. With this particular tool, it will measure out data points on converting half an inch increments as you go down. So you can get a lot of data in a very short period of time, as fast as you can drive a geoprobe point with this tool. So this will give you much more incremental granular information on where contamination is along your property line. There's also a tool called a hydraulic profiling tool. This is the one that measures formation permeability and electrical conductivity, so it can be used to infer lithology. And it will identify where the water table is, and you can also estimate hydraulic conductivity from that information. So this is a comparison that I put together of a borehole log and then an HPT point that was driven right beside it. And you can see, the fill here, you've got a fairly low hydraulic pressure, so a fairly highly conductive material. Then we hit this clay layer and you can see the pressure increases, the hydraulic conductivity drops. We've got a sand seam, and then down below we have a pressure increase again. So again, we're getting into more of those fine grain materials. But compare the borehole log here, where you have pretty crude and large zones of soil descriptions with this more precise distribution of data that's provided from the hydraulic profiling tool. And this will really help you identify things like, these higher conductivity, maybe these are sand stringers, and maybe these represent preferential flow pathways that you might not otherwise be aware of. And maybe this is where you have to load up a higher degree of remedial amendment in order to meet your discharge standards. So very powerful information. You can take that and then model it in 2D or 3D. So this is the same site. This is a fence diagram for a funnel and gate PRB that we designed. And you can see here really high flow zones up in the fill. The upper blue zone here is basically where the water table is, and then we've got more lower K zones, but we do have these interbedded sandier zones, stringers with a higher flux moving through them. And then finally down here, this dark blue layer is the silty clay till layer. So this is our confining layer. And based on this, you have a really accurate profile of how deep your PRB is going to have to go in order to key into this confining layer so that you know that you've got not only horizontal capture of the plume, but vertical capture of the plume as well. And with the information on the level of the water table, you know how high up then your reactive media also has to come. Now we'll get into a bit on some of the more recent remedial amendments. The one I mentioned earlier are these carbon-based injectables. They've been around in Canada again. I apologize for the Canada thing, but that's where I live. Since the 2015 or so, much earlier in the US, early 2000s. The first were these trap and treat products, so BOSS 100, BOSS 200. And I think this is one of the biggest breakthroughs in my career anyway on remediation, was the development of these amendments, because especially the BOSS 200 here, which treats petroleum hydrocarbons, this is the one that allowed for a truly passive PRB to be developed for petroleum hydrocarbons. That's a real breakthrough. And the way it works basically is you've got activated carbon. Here's a microscopic view of it. You can see it's like a sponge. So it absorbs contaminants, organic contaminants, very effectively out of the water. But then you have a treatment mechanism as well. So that if you think about it, without a treatment mechanism coupled with your activated carbon component, the carbon is going to become saturated with contaminants and it won't be able to absorb anymore. It's going to be useless. So you need this treatment mechanism that will then degrade those absorbed contaminants and allow those absorption sites to be regenerated, and allows it to absorb more contaminants over time. So in effect, this technology regenerates your carbon in situ and allows it to last much longer. Now, the treatment mechanism for these two in particular, the BOSS 100, which is for chlorinated solvents, it's essentially activated carbon and elemental iron, so it's absorption and chemical reduction. For BOSS 200, which is for petroleum hydrocarbons, it's carbon absorption and enhanced anaerobic biodegradation. So it's biostimulated and bioinoculated degradation of the hydrocarbons. Now, since these first two amendments came out, there's been a new generation that's come out, which are essentially catalyzed versions of these that will allow them to deal with more recalcitrant compounds, higher absorbed soil mass as well. So these ones will overcome some of the limitations that you'll have with the absorption capacity on the carbon component. Now, I'll talk a bit about bench scale testing. So we've got all of our site characterization data, so we know what our contaminant situation is and what our flux is across the plume. But maybe there's some uncertainties, or we need to have proof of concept for a regulator or for a client. So in that case, you can do bench scale testing. There's different types of tests you can do. There's sort of quick and simple batch reactors, basically fill vessels with various mixtures of remedial amendments and your contaminant groundwater, let it come into contact for a set period of time, decant it off, analyze it, see what kind of treatment you get. Or there's a sort of a flow through, more of a dynamic reactor, which is, I think, a better simulator of a PRB, because you then take contaminated groundwater from your site and you pump it at a slow rate through a column that is filled with your theoretical or your hypothetical PRB remedial admixture, and collect the effluent coming out the end and analyze that. So here's an example that we were testing 3 different combinations of remedial amendments, and this is a control column which is just filled with sand, so that we can differentiate between just the effects of the apparatus and the background media with the actual performance of the treatment media. And what you can do with this is you can look at things like overall performance. So here is order of magnitude comparison of data for arsenic, cobalt, and nickel. So here's our baseline untreated groundwater. Here's our reactor 1, which is the control. And then here's 2 different treatment media combinations. And you can see sort of the overall percent reductions that you can achieve. So in this case, we're 3 orders of magnitude reduction, which is awesome. You can also evaluate things like degree of treatment given contact time. So here's some plots showing treatment given different contact times in terms of days. So this comes into play when, say, you have actually a fairly high groundwater flow velocity. You know what your PRB thickness is or width, perpendicular to groundwater flow or parallel to groundwater flow. So if it's a yard wide, how long does it take groundwater to flow through that? That's your contact time. And you can evaluate whether you have enough reaction taking place in your PRB given that contact time to achieve your treatment objective. And then the last thing you can do is you can look at sort of the degree of treatment over time as a function of contact time and calculate a half-life. So for certain types of amendments, you can look at what the amount, in this case ZVI, that you need given your contact time in order to get that number of half-life reductions to meet your treatment objective. Because in many cases, these reactions take place on like a first-order decay curve, and you can estimate half-lives and therefore come up with a more accurate design. Then we get into sort of a more detailed design. So we've done our characterization, we've done our bench scale testing. Let's do a detailed design. So we know what our alignment is, chemical and physical characteristics of the site. We know what our mass flux is across the PRB. We know what our contact time requirement is in order to get those that degree of reduction needed. We can also then estimate the lifetime or the duration that the remedial amendment is likely to last based on that mass flux across it of contaminants. We also have some requirements for contact of the remedial amendment with the contaminants in the plume. So there's a sort of a minimum density requirement that you need, because in most cases these are either injected into the formation or they're mixed with coarse sand and placed in a trench. But you have to ensure that with any type of in situ remediation, it's a contact sport. So if you don't have enough of a minimum density distribution of your amendment, the groundwater plume flowing through that PRB might not contact the amendment, and you might not get the degree of treatment that you need coming out the other side. And then it's always a good idea as an engineer to apply some safety factors, because let's face it, you're never going to know 100% exactly what's going on in the subsurface. There's always heterogeneities, there's always some unknowns. So applying a safety factor is a good practice. I would suggest 100% factor of safety is a good idea. Typically that's not outrageous from a design perspective or a cost implication on your PRB. And then you can also get into sensitivity analysis. So there is always some variability in your parameters and some uncertainties. If you think about it, these are the two big ones, because these can vary by orders of magnitude on any given site, whereas the other ones, less than an order of magnitude. So it's important to have really good information, at least on these two. So your concentration distribution of your contaminants across the plume, and any variability in your hydraulic conductivity in the subsurface, because that's going to drive your design. Now, from an installation perspective, I said there's a few ways to do it. The basic one that is used a lot, if it's possible, is straight excavation. So you dig a trench and you backfill it with your reactive media. In this case, this was a funnel and gate design. So this is in here, this is actually a concrete wing wall. There's another one over here. So basically it's an impermeable wall underground that channels groundwater flow through this central part, which is the gate. And this design is used when there's a really wide plume that would be otherwise cost prohibitive to install a PRB across the entire length, just because of the minimum density of remedial amendment you might need. So in that case, you may want to funnel things down to a smaller zone and just have your remedial amendment in this gate portion. In this case, if this gets too deep and you don't maybe have room for cutting a slope For sidewall stability, you can go with a biopolymer slurry. Basically, this is like a guar gum or something similar that you'll pump into the excavation. As you get down below the water table, it keeps that hydrostatic pressure on the sidewalls and keeps it from caving in. And then you can place your remedial amendment mixture through this. A word of caution here on this approach is, if you think about it, when you're mixing different types of amendments, they'll have different densities. So, typically they're mixed with a coarse sand. If you're mixing something like zero-valent iron, it's much heavier than sand. If you're mixing something like a carbon-based amendment, it's much lighter than sand. So you have these density differentials. And if you create this mixture above ground and poured it, from the top down through this guar, you're going to get density separation. All your ZVI is going to be on the bottom, your sand's going to be on top, or sand's going to be on the bottom and your carbon's going to be on top. So there's some tricks to installing amendments through this type of a mixture to make sure that they stay mixed and uniform. And you can even cut these trenches through bedrock. So this is a site we recently did where it's cut through these interbedded layers of shale and limestone. If you can't dig a trench for whatever reason, stability or depth, you can go with an injection approach. So in this case, we're injecting, this is zero-valent iron along a property line through a series of direct push points. And the key to this is you want to make sure that you have as uniform distribution as possible of your remedial amendment in the subsurface. So if you think about it, and you're digging a trench and you're mixing up your backfill above ground and placing it, you've got 100% interception of the plume because you've dug down, from the water table down to the base of the plume or the confining layer, and you filled the whole thing up to above the water table with your media. So the groundwater moving through there is going to contact it. From an injection point of view, though, you don't have that cut. You're not completely transecting that plume 100%. You're injecting things. So in order to ensure distribution, you have to do something like this, where you do a series of injection points on rows that are offset with overlapping ROIs, radius of influence of your remedial amendments. And then you get sort of on a plan view, you get an interlocking set of influence with your remedial amendment when you inject it. And then similarly, vertically, you offset these points vertically again, so you get sort of these interlocking fingers of remedial amendment in the subsurface. And when you take this approach and you use a tight enough spacing and a small enough volume that you're injecting in each point, you basically will overcome heterogeneities to the extent possible with an injection approach and ensure that you have as uniform a possible distribution of your amendment in the subsurface so that the groundwater plume moving through it is going to come into contact with that remedial amendment. And this is what it would look like sort of on the ground. So you can see here, there's a series of 4 rows of offset injection points. They're just small, like a 2-inch hole basically, where we've drilled down and injected amendments vertically offset and horizontally offset. And this forms not so much like a wall underground, but a zone of injected amendment underground. Now, when you get into bedrock, it's a bit more challenging, as you can expect. You can't just drive a geoprobe point or direct push point and inject it. You have to do something else. So you have to drill a hole down into the bedrock. And what we've done is incorporate basically technology from the oil and gas sector with pressure packers. So you can do a single packer or a straddle packer type assembly, but basically you drill an open hole, it's cased off through the overburden here to keep it from caving in. You lower down your packers, you isolate off the fracture zone that you want, and you inject out into that, and you move down to the next one and so forth. Packers look something like this, where you'll have inflatable bladders at each end, and then in the middle here, this is the injection interval. So you lower this down, you inflate these, they seal against the side walls of the borehole, and then allows you to inject out just in this interval. Now, in some cases, the bedrock is not competent enough to stay open without caving in. And in that case, you can move to something like this, which is a pre-drill or a geotap type approach, where you drill down through the formation. We've used this on really tight overburden soils, like really dense tills or soils that have cobbles and boulders in it, or even bedrock. So this would be like a sonic pre-drill. We drill down through the zone where we need to do our injection, and then you backfill it with bentonite grout mixture as you pull the casings up. And this creates sort of this conduit down that will keep the sidewalls from caving in, but will allow you then to come back and do a direct push down through it. So then you can come back with your geoprobe, drive down through this bentonite very easily, and then inject out into the formation under high pressure. And this allows you then to emplace through tight materials or unstable bedrock and still do an injection approach for your remedial amendments. So then the last part is QA/QC testing. So like I said, you've gone through all this effort to properly design and install your PRB, but you want to make sure that it was installed properly. So you need to do some QA/QC testing. So historically, the old school way was you would collect samples of your sand and ZVI mixture above ground. You do some magnetic separation testing on it. You'd look at the distribution and the average, make sure it's above what your target limit was. And then maybe you would go in and do some post-installation boreholes actually through the media and collect samples and do the same type of testing. But you can actually get much better data now by using magnetic susceptibility testing for ZVI content. And if you were using a carbon-based amendment, magnetic susceptibility or separation won't work. So there's now a colorimetric dye adsorption testing that can be used for those amendments. So originally, like I said, for ZVI, you could do magnetic separation testing. But with magnetic susceptibility testing, you can do something like this. You can create a calibration curve where you generate mixtures at different concentrations by weight of zero-valent iron and sand. You take your magnetic susceptibility reading and get a correlation line. And then when you're out in the field, you take your samples at whatever frequency you want, very quickly take a reading, compare it to this calibration, and it will give you the percent of ZVI in those samples. It's very fast, very accurate, and much more quantitative than this approach, which is open to a lot of variability and margin for human error. And then with the dye adsorption testing, you can do a similar type of thing. Basically, you take a set mass of soil, you react it with a dye mixture, and then colorimetrically measure the difference in the amount of light that gets passed through that mixture and correlate that to a carbon concentration. This is a plot showing the distribution of QA/QC samples by batch with a margin of error, plus or minus 10%. That was set as our QA/QC limits on this particular site. And then you can also do an absolute measurement of what the average, in this case, BOS 100 concentration is per batch. And this is minus 10 plus 20%. But this is at 1%. So 1% was our target, and we had this range of 0.9 to 1.2%. So much more accurate measurement of the amount of carbon-based amendment in these sand mixtures. And then the ultimate validation for the PRB basically is its performance. So what is the influent versus effluent concentration? This is going to require consultants then to go back to the site and do their routine groundwater monitoring and measure things like the changes in the geochemistry. Is it shifting in the direction we want it to shift based on the amendment that we're using? Are we seeing the degree of treatment that we want? Are there indicators of degradation happening in the effluent? And what is the performance like over time? Is it consistent or is it changing? So ultimately, that's your final test. So just to summarize things, PRBs, I would say they're no longer old school, where you use sort of generic assumptions and rules of thumb, because in many cases they have failed or wasted money following that approach. There's been many new advantages in technology to make that method obsolete, and it's possible now to more intelligently design and install and validate these PRBs. And that would be coming up with a comprehensive site characterization model, doing some desktop modeling and a preliminary design. If there are data gaps or unacceptable uncertainties identified, filling those in. Maybe that's doing some alignment profiling, maybe it's collecting some K data on the site, making sure you collect the right amendment or amendments. Do some bench scale testing if you need to, if there's something unusual about your site or you need actual demonstrated proof of concept performance. Then do your detailed design, sensitivity analysis, apply a safety factor. Absolutely make sure it's installed as per the design, and do your QA/QC testing as final confirmation. And at the end of the day, then you'll learn to love PRBs like we have here. So there you go. That's what I have for you today. I'll take any questions that you have now.
Thank you. Can you hear me okay?
Yep.
Okay, great. Thanks again. If you do have any questions, please go ahead and submit those. We did have some come in while you were speaking, so we'll go ahead and start with those. And we're going to go ahead and get as many of these as possible. If we do run up against the hour, we can follow up with you. You can reach out to myself, or you can reach out to Kevin directly. So I guess one first question here, Kevin, is methods to be able to confirm the bio whenever we're talking specifically about petroleum hydrocarbon PRBs.
Right. So with petroleum hydrocarbon PRBs, if you're using something like BOS 200, which couples the anaerobic bio with the carbon adsorption, you're going to look at a few things. You're going to look at the presence of your terminal electron acceptors that you've incorporated into the PRB design. So those would be things like your nitrate and your sulfate. You're going to watch that those are still there. As soon as you see those start to deplete or be consumed, in those cases, you'll have to replenish that those TEAs and maybe the nutrients as well to keep that performance happening. And then on the analytical side, there's some pretty detailed testing of breakdown products and dissolved gases that will provide information on the actual degradation that's taken place of the PRB, or the petroleum hydrocarbons. So it's not just your hydrocarbon concentrations coming out, but those dissolved gases and the breakdown products that you can test for to show that degradation is actually occurring.
Sure, thanks. And just to add on to that, one thing that we're starting to implement more and more, and we have on several sites where PRBs have been used, is CSIA, so compound-specific isotope analysis, looking at the C13, C12 ratios, up gradient and a down gradient of PRBs. So that's something else that I think is a really cool technique to be able to pretty easily confirm occurring within the PRB itself. Okay.
Yeah.
Another one here is just on whether or not this would be recommended for any sites with product, specifically hydrocarbons.
Sorry, you broke up a bit there, Mike. Can you say that again?
Not PRBs could be applicable for a site with NAPL, specifically LNAPL.
With NAPL, yeah. So with NAPL sites, I mean, then you've got a huge mass of hydrocarbon contaminant moving through it, right? Some of the PRBs can be designed to accommodate a small amount. Like I mentioned, there's a couple products that are, well, there's one that's essentially a catalyzed form of trap and treat for hydrocarbons called BOS 200 plus, and that can deal with much higher concentrations of hydrocarbon mass. But if you had a site with a massive amount of NAPL that was mobile, you might want to combine, you do sort of like a treatment train, and you can do multiple layers of PRBs. So maybe you have an interceptor extraction trench or system up front of the PRB to pull out some of that mobile napple before it actually hits the PRB, because otherwise it's going to blow through the carbon, and especially if you've got a fairly fast groundwater flow, it's going to be difficult to get enough amendment in the ground to treat that over the long term. So if you had, like I said, a fairly substantial napple thickness at your site, you'd want to look at, I think, a two-stage system, sort of a interception and extraction, and then a polishing stage with the PRB. I don't know, Mike, what's your experience with that? Similar?
Yeah, no, I think that's a good response. And the only other thing is that we on sites with either high concentrations or high flux, series of PRBs, right? So like where you can use even using different technologies. So even like physical extraction would be one, or you could have just a series of PRBs. Your first PRB is just to knock down higher concentration, and then you've got your polish. So if you've got the room to do it, we've done that on sites where we've had just a lot of times it's just because physically inject material or apply it to be able to deal with that. So we're dealing with sequentially.
Yeah.
Another question here is just about the longevity, about the durability, and if there's a need to reapply the carbon in any of these.
Yeah, that's a good question, because I mentioned right at the beginning, ZVI has been around for a long time and it can last decades. With the carbon-based amendments, the way we do our designs is slightly different based on the contaminant. So for a chlorinated solvent site, we base them off a 20-year lifespan, and we make sure that there's enough carbon in there to absorb the massive contaminants moving through it. There's enough iron in there to degrade the contaminants, and there's sort of a minimum distribution density in order to ensure contact with the contaminants. So those types of PRBs should be good for 20 years. The other type with the petroleum hydrocarbons, because it's a biological component, that part is not as long lasting as the carbon component. So you will have to do sort of intermittent top-ups of the terminal electron acceptors and maybe the microbes as well. And that's going to be based on your monitoring, your routine monitoring after the fact. And maybe that's every couple of years, you might have to go up and top that up again to keep that treatment mechanism going. But again, you can design those hydrocarbon PRBs to last 10, 15 years. The carbon itself is going to last for a long time. You just have to make sure that the treatment mechanism will maintain the destruction pathway that long as well.
Okay. Thanks. I think we'll just have one more question, and we'll go ahead and wrap up. It was just it's regarding the basically the trap and treat, so the BOSS technologies for specifically for a PRB application, obviously, and how those compare to colloidal activated carbon.
Okay, yeah, that's a good one. So our experience with that is, the colloidal carbon is just that. It's only the carbon component, right? So you have the absorption mechanism, but you don't have a coupled, an integral treatment mechanism that goes along with it. So it's not the best for PRB application because, as your contaminant mass flux moves through that PRB, gets absorbed onto the carbon, at some point, and probably not too far distant in the future, those carbon sites are going to be fully occupied and it won't be able to absorb anymore, and you just get breakthrough happening. The other thing with the colloidal carbon is the mass of carbon that you can actually inject is quite a bit lower. Like the trap and treat products, which we like, are they're like a particulate solid, so the masses are much higher that you can inject into the ground. So from a starting point, you've got more carbon in the ground, and then you've got the treatment mechanism that goes with it. With colloidal, you only have the absorption site and a lower mass to begin with. So I would suggest it's probably not the best for a PRB. unless you had like a really diffuse low concentration plume, maybe. But then again, you'd have to look at how long that's going to last given the mass flux across it.
Excellent, thank you.
Sorry,
Yeah.
Mike, one more thing, sorry. The one more thing I'd mention as well. With colloidal too, because it's a suspension, it will actually stay in suspension for longer. Like the particulate stuff, if you can imagine, you're injecting it, as soon as you shut off the flow and pressure, it stays where it's put. It's not going to go anywhere. So if you're injecting it in a zone as a PRB, once it's injected, it's there, it doesn't move. With the colloidal, it can take a few weeks or up to 6 weeks, I think, before that will actually settle out of suspension and accumulate on the soil particles. So you might inject it in a PRB zone, but then over the next month or 6 weeks, it's going to spread out, it's going to migrate. So it may not end up ultimately being completely where you want it to be to form your PRB. So that's another thing you'd have to take into account.
Mm-hmm. Mm-hmm. Excellent. Excellent responses. Kevin, thank you. Thank you so much. Thank you for everyone. I see most of you are still here. Again, this presentation is being recorded. It's going to be uploaded. And so if you want to check out other questions, you can reach out to myself or Kevin directly. And thank you again, and enjoy the rest of your day.
Great. Thank you, everyone.